Hi, today I'd like to tell you about Park Systems' new PinPoint mode, which allows AFM users to effectively characterize the mechanical properties of polymer components. As the industrial utility of certain polymers like plastic and elastomer becomes more established, demand for the synthesis of new materials is rising. Synthesis for new applications is achieved by mixing more than two types of polymer, resulting in what is called a multi-component polymer. In the manufacturing process, being able to accurately characterize the mechanical properties of the material is essential in order to produce a specialized end product. However, it is very difficult to characterize the mechanical properties of multi-component polymers. Because polymerization occurs at the scale of nanometers, topographic surveys do not convey what is going on inside the polymer. The mechanical properties of multi-component polymers such as elastic modulus and adhesion force occur at the nanoscale. There are two conventional methods for studying these mechanical properties. One is AFM phase imaging, and the other is force distance spectroscopy. AFM phase imaging provides a mechanical property distribution visual using qualitative contrast. On the other hand, force distance spectroscopy records mechanical data quantitatively by indenting a cantilever tip on the sample surface one point at a time. To adequately characterize a multi-component polymer's mechanical properties, it is necessary to acquire both a distribution image and quantitative data simultaneously. In making this practice possible, PinPoint mode provides the most effective method for understanding and synthesizing multi-component polymers. This new mode was developed for use on the Park NX series AFMs, allowing users to study mechanical properties at the nanometer scale, complete with accurate nanonewton force control. Let's take a look at how PinPoint mode simultaneously combines mechanical property distribution imaging and quantitative cantilever data. During operation, an AFM probe approaches and indents the sample surface at each pixel in the area to be imaged. In effect, the boundaries for the desired image act as guidelines for the cantilever. At the moment when cantilever deflection reaches the force threshold, the system records the Z height. In this way, PinPoint mode provides force distance spectroscopy data in real time, while also reconstructing surface topography. Each force distance curve directly matches its corresponding position in the reconstructed topographic image. From a single data point in PinPoint mode, stiffness, modulus, and adhesion force can be determined by an automatic calculation process in the system. After the topographic data is collected, stiffness and modulus can be calculated using a selected range of the force distance curve. Applying this data to the Hertz formula, the elastic modulus can be calculated. Finally, the adhesion force can be acquired after calculating the maximum from the baseline of the force distance curve. In PinPoint mode, these data points are collected for each pixel in the imaging area and displayed as an image. The final result is a quantitative mechanical property distribution image of the multi-component polymer. Now let's take a practical look at how PinPoint imaging works on a Park AFM. With Park's AFM OS Smart Scan, anyone can achieve high-quality nanoscale imaging with auto mode, and in most cases this mode is all that is needed. However, in the case that more precise control is required, PinPoint imaging can be operated in SmartScan's manual mode. After cantilever and laser alignment, the cantilever is brought down near the sample surface so that the desired imaging position can be found. After this, click Advanced, and then PinPoint mode. This will bring up the control panel. To be able to measure nanomechanical properties, first, a single FD spectroscopy must be checked by clicking the FD button. If the baseline is not shown in the FD curve, control height should be increased until it is. This action allows you to determine optimized vertical behavior within PinPoint mode. Now, switch into scan status. and click the Enable PinPoint button so the system starts its vertical movement based on the determined FD conditions. Then after setting a desired scan size, let the system start to collect FD curve data for each pixel point within the chosen area. Click on Start, and the main imaging process will begin. During measurement, the isolated Z movements of the probe allow PinPoint to offer significant improvements compared to conventional AFM raster scanning imaging modes, because the cantilever tip is lifting perpendicularly from the sample surface at every pixel for imaging. More accurate topographical information can be acquired compared to raster scanning, even if the sample surface is extremely delicate or adhesive. PinPoint is also easy to operate for novice AFM users and can image everything, even steep edges, and soft or sticky surfaces. To see nanomechanical calculations such as adhesion and modulus, go to Scan Data. In the Scan Data window, you can select various signal sources. These visual representations are automatically acquired in the imaging process without parameter input. Here, we can see the nanomechanical property distribution of multi-component polymer blends acquired by PinPoint mode. Adhesion and moduli are visualized within a 2.5 micrometer scan size. In the adhesion image, different forces are recognizable in the range of 0.5 nanonewton. In the modulus range, the contrast directly reflects the different moduli of different components of the polymer. Bright means higher modulus, while dark means lower modulus. As we have seen, Park Systems' PinPoint mode is a new and exciting AFM imaging solution. Through quantitative mechanical property distribution imaging, it allows a more complete characterization of multi-component polymers than was ever before possible. PinPoint mode allows researchers to acquire needed mechanical information at nanometer and nanonewton scales with highly correlated topographic registration, and allows users to accurately and easily characterize the mechanical properties of polymers.